All right, just seconds. All right, do you guys see the screen?
Yes, sir. Yes.
All right. I think everybody's here now. Let me see. 1, 2, 3. Well, let me wait another few minutes, okay? I see somebody is missing. All right, maybe not. So I can continue from the last place. And what we have discussed is the model in the literature last time I started this, which describes the maximum stress in the film as a consequence of the grain zipping process. And we talked about that the overall energy of the system at 2 grains in pitch is actually minimized by disappearance of these near surfaces of the grain by creating a grain boundary, which overall has a smaller energy than the energy of the 2 surfaces that are joined together to form this grain boundary. And also, what is necessary to say is that in this process, the grains are strained. Thus, the strained grains are the ones that actually have to produce the stress. And that's the tensile stress because they have to be stretched a little bit. And this is the cause for this huge tensile stress that we observe in the films during the electrodeposition. And in general, this is the description of the process in any type of the thin film growth. Okay. If there is something else going on, then most likely grain zipping process doesn't contribute to this, but let's put this on the side. And if we recognize that the grain size can be described some average parameter D, and we look what the literature talks about this process of the grain zipping, it turns out that maximum stress is basically described as some constant which is related to the shape of the grains divided by the diameter of the grain and multiplied by this delta gamma term. Now, this delta gamma term, and in this particular case, the subscript describes the material we have the data here for, but just, that could be, in general, any metal we are depositing. In this case, this is the cobalt iron alloy. Now, this delta gamma term is actually called the driving force for grain zipping, which is described as the difference between the surface energy of the cobalt iron and -1/2 grain boundary energy of the cobalt iron. Okay. And basically, this is so far what literature tells us about this process. Now, interestingly enough, and I'm just recapitulating what I just said the last time, is that, adding just a tiny amount of the additive, such as saccharin, for example, in this case, what you can see is the drastic reduction in the maximum stress value that you see in the film. And then adding a little bit more, here, and more, and eventually more, and somewhere around, let's say, the last curve here represents the stress evolution of the cobalt iron film for 1.5 gram per liter saccharin concentration in the solution. You can see that the maximum stress has dropped below 50 megapascals. Wow, that's really low when you think about stress in the films. This is almost called, negligible stress. And you can see just by the design of the additive concentration in the bath, we can drop the level of the stress in the film about the factor of almost 10 times, from 450 down to below 50 megapascals. Now, important thing for you guys to appreciate this particular phenomenon has only been so far observed during electrodeposition. No other deposition method has been so effective in controlling the stress in the films as electrodeposition. And this is all attributed to the presence of the organic phase or organic additives in the solution that we talked about in the previous class. Actually, previous two classes. All right. So let's go a little bit further and figure it out. Why does this happen? All right. Now, case A here is the situation where we are growing cobalt iron, for example, or metal grains, which are first deposited as small nuclei like this, and then they grow in all directions, right? And basically become a bigger grains that eventually grow and start to impinge on each other, okay? Now these grains, before they impinge, do not actually grow, and the only stress that they actually can produce before the impingement is the compressive stress related to the capillary forces, etc. But I'm going to just leave this on the side because it's not really important for our discussion. As they impinge, obviously, there's a grain zipping phenomenon. As discussed, we form the grain boundary. But due to the necessity to strain the grains in order to form this grain boundary and basically cancel these surfaces or these surfaces here, then what happens is that the grain becomes strained, and as they're strained, basically it means the whole film is in the tensile stress, which is always larger than zero. And again, just to recapitulate what I have discussed, the driving force for this process is given here, which we already picked up from existing models in the literature. Now, very different situation occurs when we have additives in the solution. Now, why is that? Well, as we deposit tiny nuclei on the surface, and these nuclei grow in all directions. I can't draw because my pen is not working really well, so I just wanna a little bit imitate a good drawing here. What really happens that instantly the surface or the surface of the substrate or the surface of the nuclei is covered with some kind of a layer of organic additives absorbing on that surface. What that really means is that now we are not talking about surface energy of the clear metal surface, or in this case cobalt iron surface, but we're talking about surface energy of the metal surface that is modified by the presence of the adsorbed additive phase, which has some coverage theta. Okay. Now, as we discussed in the previous, few classes, keep in mind that theta is function of the potential. Depending at which potential we are, closer to the PZC or a little bit further away from PZC, theta could be almost 1 or could be less than 1. Keep in mind also that the theta or the coverage of the additive is also a function of the concentration of the additive. Now, if I sit at the same potential by keep increasing the concentration of the additives, due to this Langmuir formalism that I show you, that theta is equal to BC, where C additive is the concentration additive 1 plus BC additive. You can see that I can keep increasing the coverage of the additive even if I stay at a constant potential, right? By increasing the concentration. We discussed that last time. All right. Now, that means that suddenly, when I form the grain boundary in this new situation here, the driving force for the grain zipping process will be actually this delta gamma, now function of theta, which means it's a function of the coverage of the additive surface, which is equal to, basically, very simply, surface energy of these grains covered with saccharin, which is function of the coverage, minus 1/2 grain boundary energy, which is also now function of the coverage. The reason is that we will eventually, as we zip, incorporate some organic phase in these grain boundaries. And we expected this different thermodynamic situation caused by the additive adsorption of the surface, changing the surface energy, and thus, because of the incorporation, changing the grain boundary energy, because, you know, when you zip these two surfaces covered with the additives, you basically zip also some additive molecules in the grain boundary, right? We can elaborate and expand this whole concept a little bit further, okay? How are we going to do that? Well, very simple. If we, and I show you the data for this particular case, if we say that the additives do not affect the grain boundary or the grain size much, because we already have checked this, and we can consider the grain size to be constant. And then the literature expression that we have for the maximum stress in the film, we can rewrite this, and instead of writing delta gamma for cobalt iron surface, which is clean with no presence of the additives, we can write delta gamma for cobalt iron surface, or for the metal surface in general, which is the function of the additive coverage state, okay? Because of what we just taught. Now, elaborating and expanding this delta gamma as a function of saccharin coverage, as we discussed in the previous case. What we can write now conveniently using this is called mean field approach, is that each of these terms, okay, I can express as theta times the surface energy of the cobalt iron film covered with, which would be actually the surface energy of the cobalt iron film covered with 100% saccharin, right? Plus 1 minus theta, surface energy of the clean surface of the cobalt iron, okay? So this is the extreme case when surface is completely covered with the saccharin. That's why the theta term corrects this, because maybe not all the surface is covered completely with additive. And some free surface still does exist, which only has cobalt iron, no additive adsorption. I can do the same idea and expand this grain boundary energy as a function of the coverage using the same analogy. Because when you zip, right, you zip, and in some places you have some additive, some places you don't have additive adsorption. When you form the grain boundary, you can use this same analogy and mean field approach to express this. If you do some algebra from these two expressions, you can find out that you can write delta gamma as a function of the coverage of the saccharin, which is the driving force now for grain zipping in the presence of the additive on the surface, as the linear combination of mean field approach using this same idea as a theta term, which is coverage term, times the delta gamma, which is the driving force in a case where whole surface is covered by the additives, which is the driving force for the zipping, plus 1 minus theta times the driving force for the grain zipping when the surface is not covered with the additives at all. Okay. And now, doing a little bit more algebra, if you multiply these things and so on, you can write that the difference or a reduction in the driving force due to the presence of the additive on the surface is some kind of delta gamma star, defined by the basically change in the driving force for grain zipping from surface being clean without additives presence to the surface which is completely covered by the additives, right? That's this delta gamma star. Then you can basically redo the whole expression here, and you can say that stress in the film is equal to stress in the film without additives, which is the maximum stress, minus this term here, where now this delta gamma star represents the difference or the reduction in the driving force for grain zipping due to the additives. And then times theta, which is the additive coverage. And D here is still the same meaning as we discussed. It's the size of the grain. Eventually, this is good expression. It does tell us that the coverage of the additive on the surface is actually playing important role, number one. Number two, if the theta is equal 0, then which means the maximum stress doesn't include any additive modification of the stress, that this term becomes equal to the maximum stress without additives. If this is equal 1, which is the maximum coverage that could be achieved on the surface, then this whole thing has the maximum value, and then the new stress that we should see in the film is actually minimum, because this function as a function of theta going from 0 to 1 becomes the smallest one, right? Now, if we express the theta using this Langmuir formalism and put it back here in the expression, then we have the full model of the stress, maximum stress in the films during the electrodeposition in presence of the additives, where the only importantly things that are featured is the concentration of the additives, which is this C term concentration of saccharin in this case, equilibrium adsorption constant for adsorption of saccharin on the surface B, and you have this term here, delta gamma star, which is the reduction in driving force for grain zipping due to the presence of the additives on the surface. This constant usually, again, I told you, is associated with the shape of the grains, and I think in the presence of the, if we consider the hemispherical grains, this is I think 4, or actually 8, sorry. So the final model that we use here is this one. But interestingly enough for us, if you look this data, if we measure these maximum stresses and we plot them as a function of the saccharin in the solution, this is what you get. This is also very good aligned if we are not looking at the maximum, but at some thickness, 3 microns, because the stress doesn't really change. It's a thicker and thicker the film before over at the thickness is greater than 100 nanometers. And so this green line is basically your model, where this value here is the value of your stress in the film without presence of the additives in the solution, and everything else here is basically basically constants we described. So if you look what you get from fitting the model to the experimental data, it's quite interesting. You get that this uh, delta gamma cobalt iron, assuming that you can read this from the literature, is of order of 1.125. Delta gamma star you get from the fit is about 1 joule per meter. And then you end up that from this, you can calculate that delta gamma, which is a drying force when you have a surface completely covered with additives, is only about 0.125. So the reduction of the drying force from going from clean surface to surface completely covered with the additives, meaning coverage is equal 1, is about 10 times, 1000%. So when you reduce the drying force for grain zipping 1000%, almost 10 times, what you're really doing, you almost having a negligible drive for zipping. So the zipping process becomes very, very energy costly because there's no benefit if the drying force is so low. And for that reason, the stress in the film decreases as a function of concentration, and it basically, for very large coverages or large concentrations of the additives, becomes negligible or below 50 megapascal. And that explains this thermodynamic effect where you're changing the surface energy and grain boundary energy by presence of the surface, the additives on the surface is changing the driving force for grain zipping, and that overall results in the less driving force for zipping and less stress in the films. To show you that this model is actually quite generic because it does fit other systems, here's an example of nickel iron film, which is again another magnetic material, and these are some data measured experimentally, and you can see for no additives in the solution, stress is around 450, with additives being close to coverage of 1 or higher concentrations, you get about less than 100 megapascals. So obviously about 5 times more smaller stress. Do you guys have any questions? It should be straightforward. I'll give you also some materials to read, but it shouldn't be that difficult to digest. This is very simple thermodynamic model, and it really gets the full picture about this. Now, that's now the only valid model that explains the additive effects on the stress reduction in electrodeposited films. So you can see basically on these schematics that I'm showing you here, that if this is the cobalt iron surface energy, and this is the grain boundary energy we call cobalt iron clean surface with the presence of the additive, this driving force is expected to be significantly reduced when you have additive on the surface, and for that reason, we actually have less stress in the film. Right? So that's the conclusion of this whole model. Keep in mind that the stress reduction in the film is proportional to this term here, okay, which is the decrease in the driving force for grain zipping due to the presence of the additives covering completely surface. And then this term here is actually Langmuir expression for the coverage. All right. Now, redirecting a little bit of this discussion now, we can go back and start to understand some other properties. And this is just an example for you because this already requires a little bit more knowledge on the magnetics of the material. But I just want to give you an idea of what happens once you know what additives do to the stress in the films. All right. So here's another interesting thing. If you plot coercivity, and if you remember what coercivity is, this is the external of the value of the external magnetic field, which is required to reverse magnetization in the soft magnetic material, right? And we say the softer the material, the smaller the value of coercivity or external magnetic field that is required to reverse the magnetization. So smaller HC is better even if we talk about um, soft magnetic materials. So what you have here, we plot films coercivity as a function of the average stress, or basically maximum stress in these films at the thickness, which is, for example, about 100 nanometers. So basically, we take these values here and we plot them against the actual coercivity values of this film, right? Interestingly enough, guess what happens? If you see here the stress in the film as it drops, the coercivity in the film drops. So, as we discussed before, if you remember that we know that incorporation of the additives is directly linked to the decrease of the film coercivity, if you remember what we talked last class. And you remember that we like more to have molecules of the additives incorporated because this is more effective action of additives than creation of these sulfide particles. And now we see another evidence of the additive benefit. The stress decrease in the film also benefits the coercivity decrease in the film. Now, if you look the expression for coercivity, which is something that comes from the literature of magnetic materials, you can see that is a function of the stress in the film. So additives decrease the stress in the film and the coercivity actually drops. Now, if you think about why we like molecules better than the sulfide particles, it's a very simple thing. If the molecules are incorporated, they effectively end up at the grain boundaries as a whole molecule. As such, they decrease the energy of the grain boundaries. And they, or actually, sorry, not decrease, they increase the energy of the grain boundaries with respect to the existing energy of the grain boundary, which is for the clean film. Why? Because they somehow do not allow formation of the bond because the molecules is kind of get trapped in between two atoms and it prevents the bond formation in the grain boundary. So connectivity of the atoms in the grain boundary is poor when you have molecules trapped at the grain boundaries. And that results in this shift, actually an increase of the grain boundary energy in the presence of the saccharine adsorption. Okay. At the same time, as we discussed last time, the presence of the additive decreases the surface energy of the film because those dangling bonds that are high energy are saturated by the presence of the foreign molecules of the organic phase adsorbed on the surface. So that's this dual effect that results in the reduction of the driving force for grain zipping process. So now, as you can see, a further decrease of the stress seems to have an opposite effect at one point, because you can see we reach kind of minimum coercivity for the films that are of about 100 megapascal stress, let's say, and then we further decrease by adding more additives in the solution. We further decrease the stress, but guess what's happened? Stress, the coercivity starts to increase. Why is that? Well, if you have just a few additives that mess up these bonds at the grain boundaries, it's actually a positive effect because the grain boundaries are not having connectivity of the atoms at the grain boundaries is prevented. But there's another problem. If you put too many of them, too many, and this is here, this part here, if you have too many of them, what happens is that you start magnetically decoupling the grains because the amount of the phase which is organic phase here at the grain boundary, is non-magnetic phase. And what it does, it decouples the magnetization between the grains, and they are not talking to each other anymore. And this type of the structure, which is kind of decoupled by the non-magnetic phase, suddenly becomes acting like magnetically harder, because when you flip the magnetization in one grain instead of helping flipping the other grains, because they are not magnetically talking to each other, actually they don't flip. They require more energies to flip further, and this why you see this kind of slight increase. So it's a kind of question of optimism. So what that really means after this discussion is that if you look, for example, this data, I just want to show you this film here with 1.5 grams per liter of saccharin, although it has the lowest stress, not necessarily will have the lowest coercivity. The lowest coercivity actually will be for the film that is about 100 and some megapascals, which is basically the film that is probably 0.2 grams per liter saccharin. So although the control of the stress does have benefits for mechanical performance in terms of the, you're on the safe side from film delamination and other issues, at the same time, from the magnetic point of view, adding additives, too much additives in solution eventually will not make your coercivity keep dropping. So the overall properties of the film are not necessarily one-sided with respect to the additive concentration, because it's a trade-off. You want to have a low stress, but if you keep adding additives just looking the stress control, you might sacrifice some coercivity, meaning the films might become a little bit harder than you want. Okay, so that's this magic about when you work with some materials and you know all this stuff, then nobody can tell you, oh, this is magic or something. There's no magic here, it's pure science. And so if you understand this kind of a basic concept, you already can handle a lot of problems in electrodeposition when it comes to design of the effective baths or additives for electrodeposition process. All right. Now, how do we do with the time?
We have 50 minutes.
How many?
50.
50.
50.
All right. So now I'm going to tell you a story that actually, in some sense, cancels all the benefits of the additives, because we saw that additives are good for stress control, for magnetic properties control. We heard about that additives do incorporate in the deposit, and there's a kind of correlation between additives incorporation and magnetic properties control. Then we see that they control the surface energy of the film and grain boundary energy of the film, which is again beneficial for our stress situation. Okay, but nothing comes free, all right? And the reason is that corrosion properties of the materials that we electrodeposit in the presence of additives are usually much worse than the properties of the materials that we electrodeposit without additives. And that's, typical for copper, for nickel, for many, many materials that use organic additives, which serves the purpose of stress control or softness control or roughness control, etc. Okay. So now I'm going to give you an example about that and show you that we do understand this too. And in the literature that I'm going to give it to you to read, you will understand that design of the additives is actually quite complicated in a way that you need to know exactly what your film is supposed to do. If your film should not have any protective properties, for example, and it's purely focused on magnetic performance, less on mechanical integrity, then you just go about minimizing, for example, a softness. and maximizing the moment. If the film's supposed to go through some cycles of thermal treatment, then you need to be worried about the stress in the film. So, but then if the film needs to also be having some kind of corrosion resistance and stress, low stress, and good magnetic properties, then you have this trilemma that you need to solve. The trilemma is actually because whatever additives do to help you with magnetic properties, they also do not help you with corrosion resistance. Now, why is that? Here's an example. This is a corrosion potential measurements of the cobalt iron alloys which are sputtered and which are deposited without any additive in the solution. And you can see corrosion potential is quite high or close. It's about minus 0.2. Now, without going and making this class a corrosion class, I'm just going to give you an idea what corrosion potential means. Right? Corrosion potential here is measured in neutral solutions. All right. So this is the reversible potential of your metal. Okay, equilibrium potential right here. And this is your reversible potential for oxygen reduction. In neutral solutions where we have 10 to the minus 7 concentration of H plus, these alloys corrode by the oxygen reduction reaction. And the reaction that is associated with this is the log scale, right? So this is current, log current, right? These alloys corrode by activation control part, which means this is a straight line in a log plot, right? Now, what is important for you to appreciate is that if the corrosion and this is the curve that shows the reaction of the oxygen reduction, where the intercept is the corrosion potential. Now, if the corrosion potential is closer to your reversible potential of your metal, your corrosion rate is high. I just want to show you something. If, for example, this activation control is very slow, okay, which means it has this low, corrosion potential will be here. This corrosion potential will be more positive than this one. But the corrosion rate, as you can see in this case, the value of this log I will be much lower than the value of this log I. So in this case, we like to have corrosion potential, which is further away from the reversible potential or equilibrium potential of your films. The equilibrium potential of the cobalt iron is somewhere here. So this corrosion potential is good, which means it's a low corrosion rate. This corrosion potential is actually pretty bad, which means you have pretty high corrosion rate. Okay. Now, if I can explain you this without going too much into corrosion, I can tell you that the ratio between corrosion current of the alloys with presence of saccharine, which are deposited in the presence of the saccharine in the solution, divided by the corrosion current of the alloys which are deposited without presence of the additives in the solution, scale, this ratio scales with some terms here, which I'm not going to discuss in a moment, but it's proportional. This exponential term is to this delta E corrosion, which is basically the difference here. Right? And what that really means is that guy will corrode much faster, or the ratio is much bigger if this term here, delta E corrosion, difference between these two corrosion potentials is much larger. And this is a very big problem because, yes, we do get benefit of the additives for many properties, but look, if you just play with this, you will realize that this is going to corrode 10 times faster just because it's the alloy is electrodeposited with the presence of additives. This ratio here is plotted as a function of this delta E corrosion, which is this difference here. And you can see if, let's say, my electrodeposited alloy has corrosion potential here, which is around 0.2 volts difference, or 0.05 volts difference, it's, probably negligible difference in the corrosion rates. But here, 0.3 volts means about factor 10. In reality, that means your device will last about 10 times shorter in some corrosive environments than the device that is made by alloys which are sputtered or electrodeposited without any saccharin. And when I worked in Seagate, that was actually a huge problem because we had about 90% of the devices with cobalt iron failing after 3 months in humid weather. And since our production was in Thailand, where the humidity is about 100% most of the year, our products, which were ready to be shipped, had to be put in storage rooms. And the storage rooms were not air conditioned. And just by waiting for shipping, they would be corroding, and we would get huge reclamation calls from Dell, from all these companies that make computers, because we would deliver the hard disk which would not work. I was in Thailand for 2 weeks trying to fix this problem, and eventually that's steered the interest to actually understand why the corrosion properties and how the corrosion properties deteriorate as a function of additives. All right, so here what we have is the corrosion potential. This is a test solution for the corrosion potential. And what we really measure is the corrosion potential of the different samples which are produced by solutions which are identical, but they only differ in concentration of additives. They, in this case, saccharin they have. And these are 2 runs. One is with a rotation of 300 RPMs and one is without rotation. And you can see drastic change in the corrosion potential with a minimum addition of saccharin. And as you keep increasing this saccharin, then you can see that there's a little bit more decrease, and then eventually kind of levels out and keeps steadily going back. The same observation is for the 300 RPMs. If we try to plot this corrosion potential as a function of the incorporation rate of the whole additives and as a sulfur particles or as a whole molecules, we see interesting thing. There's a linear relation, and then there's another parallel linear relation too. It doesn't really give you an idea of what's going on. Now, trying to understand what's going on, we have from the corrosion science, we know that the oxygen reduction current is diffusion limited. And that means that could be expressed as a function of concentration of the oxygen in the solution. And this is diffusion layer thickness, this is diffusivity of oxygen, and this is just a Faraday's constant. We also know that if we dissolve in cobalt iron film, we can express the dissolution current as the product of the exchange current density for cobalt iron dissolution times this exponential term, where this is anodic coefficient, Faraday's constant, RT, and this is E corrosion minus equilibrium potential of cobalt iron, right? And so if you play with these two, you can end up basically getting the value of corrosion potential for these alloys as a function of the diffusion limited current for oxygen reduction, exchange current density for cobalt iron dissolution, and reversible or equilibrium potential for cobalt iron alloy. That's just the corrosion science. I don't want to really go into this, but so you understand where this equation comes from. And this pretty much tells you where the corrosion potential is a function of these two basically reactions. And the shift in the corrosion potential due to the mixing is basically that you're increasing the diffusion limited current for oxygen reduction. All right, so first thing we've done, we have taken these old films and we were just applying linear polarization, which means we would just go and apply more and more positive potentials, and we were looking how these films dissolve. And those are the dissolution peaks. And interestingly enough, this black curve is the alloy that is produced without any suckering in the solution. And you have to really go about 400 millivolts more positive to see anodic dissolution of the film. While most of the alloys that actually are deposited with saccharin in the solution, when you try to dissolve them, they start dissolution pretty much all at the same time. Now the dissolution peaks, obviously, here, are not all at the same position, but dissolution starts about at the same potential. All right. If you analyze this initial part of this course, which is the linear part, you can extract from this basically corrosion, very important parameters in the corrosion, which is called charge transfer resistance, and we talked about this, if you remember. And that's what we've done. This is a charge transfer resistance as a function of the saccharin concentration expressed as this term, which represents the coverage. So this is basically like a coverage of saccharin, right? And here's what we find. This term here, I just forgot to tell you, is the exchange current density for dissolution of the saccharin, anodic dissolution. And you can see the higher the coverage of the saccharin, the higher exchange current density for dissolution, which is very important, which means, the more coverage, the more additive on the surface you have during electrodeposition, it's easier actually to dissolve this alloy after that, okay? Same thing here. It's just the same story, just the opposite parameter is the charge transfer resistance drops as you have more additive on the surface during the electrodeposition, and this charge transfer resistance is during the anodic dissolution of these films, right? But what is cool is that obviously this linear relation here that we see can be also recovered from this part of the curves, which is from the tuffle slopes. So we get two identical conclusions, one obtained from the linear part and one obtained from the tuffle part of the slopes. And they tell you the same story. All right. So it seems like that when we do electrodeposition with additives, they do incorporate and they do affect the additives, the alloy ability to resist the anodic dissolution. More incorporation of the additives, which is proportional to the coverage of the additives, is likely to cause poorer resistance of the additives to the dissolution, basically. And you can see the charge transfer resistance drops or exchange current density increases. All right, so let's put this in the map. This is our general model that I show you from the corrosion literature. And what we want to say is that it looks like from our experiments is that our exchange current density for corrosion of anodic dissolution of the cobalt iron can be expressed as a linear function of the electro reduction rate of the additives. Why? Because this term here, as you remember, is proportional to the theta. And so molecule incorporation seems to not affect the corrosion, but only the electroreduction, because we see the linear relation with coverage, not with theta times 1 minus theta. Okay. And that means we can express the exchange current density during anodic dissolution of the films as a function of the saccharin when we replace this theta by this Langmuir term, and then instead of whole thing, we write this proportionality constant times this constant, which is electroreduction rate constant of the additive. So this is becoming some new constant, and we can write this whole thing again in a little bit more condensed form. All right. So now, interestingly enough, if we look the onset of the dissolution of these alloys during the anodic polarization, what we see that the alloys that do not have any presence in the additives in the solution, which we electrodeposit as a pure alloys, completely differ when it comes to this onset of the anodic dissolution, where all additives, pretty much regardless how much saccharin you have in solution, have kind of common anodic onset dissolution potential, and the alloys that do not have any that the electrodeposited without saccharin in the solution actually completely look different, basically. And so what that really means is like the two different phases here are corroding. One that is actually super high corrosion or anodic dissolution potential, and one that has super negative anodic dissolution potential. That tells you already something. So in our general term, we replace the exchange current density for dissolution by our new expression that we developed. And we assume that this equilibrium potential of our alloys when we electrodeposit them with the saccharin changes significantly and becomes some average value, which is the same for all alloys electrodeposited with saccharin in the solution. This is the diffusion limited current for the oxygen reduction. Everything else has been mentioned. Okay, so this we know, this we know, this we know, this we know, and we can do an experiment. We can get this from the experiment. We can get this from the experiment. And guess what? This is the model. And this model we apply for all these points that are showing basically for the alloys that electrodeposited with presence of saccharin in the solution. And you can see that we can actually explain the corrosion potential dependence just by incorporating this whole additive concentration business in the description of the exchange current density term for anodic dissolution of the alloys. And this term here, which is only basically 1 point, is just cobalt iron alloys that are electrodeposited without any saccharin. So you kind of get a very nice understanding right now that basically, if we keep increasing concentration of the additives, we will be decreasing the stress in the film. We will not be getting the softest films because we know there is an optimum in concentration that gives the softest film. So more additives doesn't mean softer films. There's an optimum. And we will be getting films that corrode faster. So overall, the conclusion of this whole discussion about additives is that we do understand that additives help us with the softer alloys, and we do understand that seeing more molecular incorporation is better than less molecular incorporation, which means we want to design our bath where we maximize molecular incorporation of the additives. And you remember last time we discussed which part is that. That's number one. And number two, more additives decrease the stress, but at one point starts to hurt you because it will start building up corrosivity. And the last thing is that more additives make the alloys less susceptible, or actually more susceptible for corrosion, if we are just looking corrosion potential discussion. And overall, what it really tells you is that understanding the additive effect is understanding the all phenomena involved in the action of the additives with the metal surface during electrodeposition. There's no doubt they do incorporate in the deposit. There's no doubt that this incorporation benefits certain properties. And there's no doubt that modification of the surface thermodynamics, which is the surface energy of the film and grain boundary energy of the film, decreases the driving force for grain zipping process. So in some sense, if our goal is to produce ultra soft films and don't care about some other things, we will maximize the additive content in the bath. But if we have to worry about corrosion properties, we have to find some kind of optimum concentration which will give us an alloy which is relatively low stress, but for example, will have a decent corrosion property. And the third thing is that the whole business about additives is not a myth. It's actually a scientific, well understood problem. And the only thing I'm going to add to this discussion next time is the additive effect on the grain boundary, grain size, which not necessarily always shows up. And I'll talk about this a little bit more. But there is an additive effect which people commonly associate with grain refining, which means additive makes smaller grains. And I'll explain you how this can be discussed within a framework of the nucleation story that we have talked about several lectures ago. But with that, this is pretty much all what I have for today. Do you guys have any questions? All right, so Peter, you can start.
I only had one question regarding the stress, Professor. So the stress is reduced with adding additives, right? But is it the same for the stress of the film is the same thing as the surface tension? Will it be reduced with additives?
No. Stress in the film is not surface tension. Surface tension is the surface. It's surface phenomenon. Stress in the film due to the grain zipping process is the bulk stress that basically puts the grains under tension. So it's two different things.
Two different things.
But,
Okay.
But very important thing for you. Adsorption of the organic phase on the surface does change the surface tension too, which is the surface energy, basically, if you ask me.
Oh, yeah.
Yes. And that's very important thermodynamic fact that actually is responsible for decrease in the driving force for grain zipping process. So yes, but make a distinction between the bulk stress, which is in the film, okay,
yes,
and surface tension, which is the surface energy type of the thing, okay.
Okay. Yes. Okay. Thank you, Professor.
Any more questions? All right. So Monday we will discuss the grain refining, and we're going to probably later on I'll have more examples on additive action when I talk about superfill. But I want to move to discuss a few more fundamental things, and pretty much by mid-March start to talk about more specific stuff once we cover the fundamentals. So I'll see you guys Monday. Okay. Thank you.
Thank you.